Space optimized 0-1 knapsack. We are going to build on this idea of space optimization over whatever we learned in the last lecture. So whatever you see written here, all these are what we learned in the last lecture. We are going to see what is the idea that we can use here in order to optimize the total space that is used in 0-1 knapsack algorithm. We learned that total time taken by 0-1 knapsack is order of n into w, where n is the total number of items that you have in knapsack, that is items you can have in knapsack, and w is the total capacity of the knapsack. What about the space complexity? Space complexity is also the same order of nw, and this is because of the dp table, that we had a dp table. Because of this dp table, we consumed order of nw space because it had n rows and w columns. Because of that, we used nw space. What are we going to do now is, we are going to see if it is possible to decrease the space from order of nw to order of w. If we can do this, that will be a space optimization on the algorithm. This is what we are going to do. Let us understand some facts about the algorithm that we used, and from there we'll try to find those small points using which we can decrease the space. First thing is, total space used was n plus 1 cross w plus 1 matrix. That is the total space that we used. How did we use it? We used it in initial steps. It was just initialization to zeros, but the most important step, that is, one is here and one is here. If you see both of these steps, there is something to be noted here. That is, whenever you want to update any particular row, you are only looking at the row right above it. You are not looking into any of the other rows, but only into one row, that is I minus 1th row. You may look into any entry in the I minus 1th row. For example, here you are looking into any entry, that is j minus wi, could be any entry towards the left in the I minus 1th row, but you are sure that it is only in the I minus 1th row. You are not using any other row. Even if you see whatever you did in the table, while filling any particular row, you only looked at the row just before that. You never looked at any of the previous rows. This means once you are done with a row, you only need to keep track of the row just before your row, and whatever be the other rows, those are not necessary. So you need not ideally store this complete table. Instead, you could just store one row and make the changes accordingly. This is the logic we are going to use. So let us see how you can implement this logic. So in order to implement this logic, first thing is, instead of the matrix, I am going to convert it into array. So dp n plus 1 w plus 1. Instead of this, we'll be just using dp w plus 1. This is a one-dimensional array. Okay, w plus 1. So from matrix, we are moving on to array. What are the things we have to keep track of? One is this n plus 1 is gone, only w plus 1 remains. There is no dpij now, it is simply dpj. What is the initialization? All the entries will be initialized to 0. So all the dpj's will be initialized to 0. You don't have this table, you simply have an array. All the entries initialized to 0. This is what you have to begin with. Then what is the next step? Let us see how to modify this step in order to change from a matrix to an array. So the first thing, you are considering that whatever entries you have in the matrix, this is your previous row. That is, presently you are updating the present row. You are considering that all the entries in your array are the entries of the previous row. Considering this, you are updating. So let us say you want to make this updation. dpij is equal to dpi minus 1j. So you are already assuming that whatever is your present dpij, this is your previous I minus 1j. So you need not do any updation in this step. Instead of doing this updation, if the weight of this particular element is more than the capacity of the matrix, You just don't have to do any operation. Don't do anything. It is same as updating with the value in the previous row. So you are doing some space optimization here, and even your mathematical calculation became easier because you don't even have to copy any value. Instead, you can simply leave it and move on to the next operation. What is the next case? In case it is less than or equal to j, that is the weight of this item is lesser than or equal to the capacity of the bag. In this case, you have two options. One is you can include the item, that is you can include the item, then it is this one. Otherwise, if you are not including the item, then it is this one. So as we discussed in the previous step, if you are not including the item, then dp I minus 1j is whatever value you are presently having. So you don't have to do anything here. Whatever is your value that is present in the array, just keep it untouched. Don't do anything. That is, you can, instead of I minus 1j, you can say dp of j. Here also you can write it if you want. Instead of dp ij is equal to I minus 1j, you can write dp of j, let us say dp of j is equal to whatever was previously dp of j. Simply write dp of j equal to dp of j. You don't have to do anything here. I simply, in order to convert the previous algorithm to this algorithm, I simply wrote dpj is equal to dpj. That means nothing to be done. Just keep as it is. What about here? Instead of writing dp I minus 1j, you can simply write dp of j is equal to maximum of, one option is this element itself, dp of j, or in case you are adding the element, that is ith element is being added to the knapsack, in that case you have to count value of ith element. Yes, you have to add the value of ith element, plus instead of dp I minus 1 j minus w1, that is from the previous row you were taking j minus with column. Instead of that, you can simply do dp of j minus wi, because your present row is whatever is in your previous row's value. But there is something to be taken care here. What is it to be taken care? Let us say you are simply filling rows like you filled here. If you are following the same way, then the problem is while you are filling, you will be updating some values. That is, for example, let us say this particular row. While you are filling this row, or let us say some other row, this one, second row. While you are filling this second row, you would have updated some values. That is, if you are filling this particular row, while filling, you would have updated many values. For example, you updated this value from 2 to 3. If you are using only array, initially the values will be those of this row. And then you would have updated this value from 2 to 3, which means this 2 is no more available because this is an array. In this particular case, it is a matrix, so you have the previous row. But if it is an array, like we discussed right now, a one-dimensional array, then this value 2 is updated as 3, which means later when you are trying to update other entries of the row, if you look back at this particular entry, you will be seeing a wrong entry, because ideally you should be doing the updation looking at the previous row. But here, because you updated with the values of this row, you will be making wrong updations after this point. So how can you tackle this problem? In order to tackle this problem, there is a very simple trick. What is the simple trick? Just give a small thought. You can easily find this out. The simple trick is, instead of filling this array from left to right, just fill it from right to left. If you do in the reverse order, this whole problem is solved. Why is it solved? Because whenever you want to fill any particular point, let us say you want to fill this particular block. If you want to fill this, what are the values you are going to look? One, you are going to look the block right above it. So in case of array, it is the same block. So there is no problem. Whatever is the value there, that is the value that is previously existing. So instead of 5, you will be having this 2 in that array point at that point before updating 5. What is the second value you are going to check it? Second value will be something which is to the left of this. It could be any depending on the weight of the item, but surely you are not going to look any block to the right of this. You are only going to look into those blocks which are to the left of this in this row. So when you are dealing with an array instead of a matrix, what do you want to do? Instead of making updations from left to right, start from the rightmost block. Start from the rightmost block and keep editing. In that case, when you are editing any particular block, let us say you are editing this block, you will only be looking at the blocks on the left, and whatever be the blocks on the left, those are not modified in this iteration. Those were modified in the previous iteration, which means it is same as the values of the previous row. So because of this, instead of updating the array from left to right, if you use this simple idea of updating the array from right to left, you can use a single array and do this complete problem. So now let us go back to the algorithm and see. This whole thing will work as it is. Finally, what do you want to do? You have to take the last value, whatever is the value in the last column, last particular block. So when you're taking that, only thing is, whenever you are running this loop, make sure that you are running from right to left. Do not run from left to right as we learned in case of matrix. Simply run the loop from right to left. Then you can simply use single array. In that case, here you don't have to make updation. Here also no updation is required. In case the value is larger when you are using this particular element, that is the only case when you have to make any updation. What happens here? In this case, time complexity will be same as the previous one, that is order of n into w, but the space complexity of the algorithm will come down to order of w. So this is where you are going to gain while doing space optimized dynamic programming for 01 Knapsack. So keep in mind, whatever we learned previously for 01 Knapsack, that was having time complexity order of nw and space complexity also order of n into w. This time we decrease the space complexity by using a one-dimensional array instead of the two-dimensional matrix. So our space complexity came down from order of nw to order of w. But keep in mind, the logic is same, time complexity is same, just that the way we were storing the values in dynamic programming, that got altered, because of which the space complexity came down. So this is it about space optimized 01 Knapsack.